All right, so we are going to go ahead and get started today. Thank you so much to everyone who is coming and attending. We're looking forward to this conversation that we are going to have today about AI.
Excuse
And
me, but I cannot hear you.
oh, okay. Are other people having any issues hearing me?
I'm wondering if you can turn up the volume at all.
It doesn't seem to be that other people are having an issue hearing me, so I don't know if you can turn up your speaker maybe.
I'm fine. Yep.
Okay. Yeah, I think that if you can possibly turn your speaker up, that might be just because
Right.
it seems like it's working for me. So we're going to go ahead and do an introduction, and then JD's going to get into his presentation. So again, thank you to everyone for coming today. And Dr. J.D. Jayaraman is the interim dean of the NJCU School of Business and associate professor of finance. He was a former faculty fellow for the Mellon DEF CON grant, which myself and Dr. Jennifer Musial are the co-PIs of. And we are very excited to have him today and to speak about AI. And thank you to JD for speaking and to the Provost's office for also helping to support this event today along with the Mellon DEF CON grant. All right, JD, whenever you're ready.
All right. Good morning, everyone. Nice to
Morning.
see all of you. I think I know most of you, so that's great. So in the next hour, we'll work on some theorems and proofs as relates to machine learning, right? So that's what we're going to do. Got to make you work for that $50 gift card, right? No, don't worry. We're not going to do any theorems, no proofs, nothing. We're going to talk about things that are more intuitive, common sense level, and hopefully you get to take away some concrete ideas to improve your productivity with AI, right? So let me share my screen and we'll get started. All right, so the agenda for today is two parts. So the first part, I'm going to talk about how LLMs work, right? So that's the first part of the talk. And then the second part, I will talk about how we can use the LLMs better, right? So in the first part, I'm essentially going to try to give you a high-level overview of how these LLMs work. And in the second part, we'll drill down into specific techniques and tips that you can use to better use these LLM models, right? So the brain behind LLMs are neural networks, and I'm sure all of you have heard of neural networks. So just to give you an idea, the neural networks are essentially computational models that are inspired by the structure and function of our brain, right? So they are designed to learn patterns in the data. The key thing about neural networks is that the ability for them to learn these patterns is done automatically, right? So without explicit programming. So in 10 years back, 15 years back, when I went to undergrad for computer science, we actually had AI back then, right? This was almost 30 plus years back. And the way we approached AI is so different from the way we approach it now. The AI was actually more explicitly programmed, right? So you told the robot, for example, you got to move 5 steps forward and then move left another 5 steps to navigate this workspace. The robot didn't learn by itself, right? So that's the key difference here is the neural network is able to learn these patterns automatically without any explicit programming. So the inspiration for this is, of course, our biological neuron that the brain is made up of. And these neurons receive signals through what are called dendrites, and then they get processed in the cell body, and then the signals get transmitted along the axon to other neurons via these synapses, right? The strength of the connection at that synapse determines how much influence one neuron has on another neuron. Okay? So this is basically how the neurons in our brain work. And our objective here with neural networks is to create an artificial neuron, right? So we create a mathematical artificial neuron that looks very similar to the actual biological neuron, right? So the neuron has inputs. There are weights. The inputs are essentially what you feed into the neural network. It could be anything. It could be just spreadsheet type data that we have, or it could be images, it could be text, it could be audio, it could be anything, right? And these are the inputs that go into the neural network. And each of these inputs has a weight associated with it. So these weights determine the importance of that input, right? So how important is this input? And the biological analogy is the strength of those synapses, right? So the artificial neuron takes these inputs and multiplies it by their weight and sums it up. So as you see in this diagram right here below, these are the inputs. Each of these inputs have the weights and they get summed up. And the output of that sum goes to what's called an activation function. So this activation function introduces the nonlinearity into the network, right? So it transforms the summation into an output. So here you're talking about a model that can introduce a lot of nonlinearity into the modeling. That's the key thing about neural networks. They can capture a lot of nonlinearity, right? If we did not have this nonlinearity, then it essentially will boil down to something like a linear regression model that most of us are familiar with, right? Which is less powerful. And so that's the use of the activation function. It converts this summation that's produced. You can think of that summation being produced in the cell body of the neuron, and that gets transformed into an output. And this output gets passed on to the next neuron, right? So that's the basic structure of the artificial neuron that we create that tries to mimic the biological neuron. Please feel free to stop me if you have any questions. So the architecture essentially boils down to an input layer that receives the raw data. Then the output of that input layer gets passed through a bunch of hidden layers. So again, there's a lot of terminology, and I'm trying to introduce all the terminology. So when you read about these things, when you read about what's a hidden layer, you kind of get what the article is saying. So it gets passed through a bunch of hidden layers. And then there's a output layer. So this is a typical structure of any neural network where you have the input layer, a bunch of hidden layers, and then an output layer, right? So these hidden layers essentially do a lot of work. They essentially extract these patterns, they learn these patterns, and for example, it can take as input an image, and it'll try to figure out whether extract certain features from that image and try to um, figure out whether, for example, a classic example is identifying whether an image is a cat or dog, right? So the output layer puts everything together and comes up with an output, maybe a 1 to indicate that it's a cat and a 0 to indicate it's a dog, right? So this is typically the structure of a simple neural network. Of course, the present day LLMs and other sophisticated networks have very complicated structures, but at the end of the day, they kind of fit into this model, really. So we won't go into any sort of very technical deep dives into the actual LLM architecture, but I want to give a sense of, okay, what's a neural network? What's the neural network architecture? And the idea is the LLM is a more complex version of the simple neural network that I'm trying to illustrate here. Okay. So this type of an architecture is typically called a feed-forward architecture, right? So all the arrows that you see are pointing in one direction. So the input comes in, it goes through the hidden layers, and out comes the output, right? It's all in one direction. So this is typically referred to a feed-forward network. There are other types of networks that are more complex that have kind of loops in there, right? So that's, again, there's lots of different variations on this architecture. All right, so let's get to this key question of how do these neural networks learn? So the way they learn is, to give you an analogy, think of, let's say, an audio equalizer, right? In a concert or in a, you have these huge equalizers where you kind of, turn the dials and make sure the sound that you desire is what is produced, right? So the idea here is you're going to be tuning or turning these knobs, right? Uh, and the first time you do it, the sound may not be as good, but as you keep turning the knobs, you get iteratively to the desired output, right? So it's kind of similar with neural networks as well. The input data goes through these layers, as we talked about, right? And this is called forward propagation. Then you get output from this neural network, which is essentially a prediction, right? So you come up with some predicted value. And what you do is you compare that predicted value with the actual value. So you have in the data, you have both the actual value and the predicted value, right? So the neural network takes that data, produces a prediction of the output, and then you compare it to the actual value, right? And you compute an error. So the difference between the predicted value and the actual value is going to be the error, right? And that error, common sense tells us we need to reduce that error, right? So what we do is the first step to reducing that error is to actually quantify that error, right? We need to calculate that error and quantify it. And that's the job of this loss function, okay? We have something called the loss function, which quantifies the error in the prediction, okay? This loss function could be something as simple as just predicted value minus actual value, right? Or it could be, for those of you who are familiar with regression, it's the loss function for a regression is the mean squared error, or the root mean squared error, or the sum of squared errors. So these are examples of loss functions. So the job of the loss function is pretty simple. It needs to quantify the error, and the type of loss function you use depends on what type of data you're dealing with, right? And what type of model you're trying to create, what are you trying to predict. These drive the choice for loss function. So now that we have quantified the loss, what do? We need to make the loss as small as possible, right? Or the error as small as possible. So we go back, right, and turn these dials. We keep turning these dials until the error reduces to an acceptable level. Okay. So this is typically called back propagation. And the dials you can think of as these weights that we are going to adjust, right? So we are going to adjust these weights in such a way that the error gets smaller and smaller and smaller. Or in other words, we are going to minimize the error. Okay. So that's essentially how it learns. So when we say learn, it essentially is trying to minimize the error and change these weights. What are we learning? We are essentially learning these weights, right? So what are the optimal set of weights that give us the minimal error, right? Once we figure that out, we have a good model that's producing a very accurate result, right? So that's the concept of learning here. So I hope that makes sense. Any questions on that? So it's an iterative process, right? So if for those of you familiar with math, this is an optimization algorithm, like a minimization. So you minimize the loss function subject to certain constraints, and that's what it actually boils down to mathematically. All right. So that's how these networks learn. So now let's move on to how do these large language models actually work. And as I said before, large language models are nothing but neural networks, right? They're pretty sophisticated neural networks, but at the end of the day, they are just neural networks, right? So the particular architecture that's used nowadays in the LLMs that you see, like ChatGPT and the Google Gemini and every other thing that you see, is a variation on what is called a transformer architecture. Or we won't go into detail there, just throwing out the terminology. So how do these LLMs work? What they do at a very fundamental level is they predict the next word in a sentence. So they are taking some text as input, then they're processing it, and they're predicting what comes next. Right? The prediction could be a single word, it could be a sentence, it could be an entire document, it could be an entire book, right? So it could be anything, like you've seen when you put something into ChatGPT, you get a large amount of output, right? So how do they produce that output? Essentially, they come up with a probability for each word that could come next, right? So, for example, in this diagram, it shows the boy went to that's the input. And what's the next word? There's a 0.1 chance that it could be the cafe, 0.05 chance that it could be the hospital, and 0.4% chance that it's the playground, and so on. So it essentially produces a probability for every possible word in the vocabulary, in the English vocabulary, essentially, right? And the simplest way, one of the simplest way it decides to choose the next word is by going with the word that has the highest probability, right? So in this case, playground. So the output it's going to produce is the boy went to the playground, right? So that at a very fundamental level, that's what a language model does, right? Any questions so far? All right. So now, next question. We know that computers cannot directly work on text, right? So computers understand numbers. They essentially bits and bytes and zeros and ones and so on, right? It doesn't actually understand text directly, right? So how do we get the text into a form that a neural network actually can understand? Right? So that's the next question. The first step in that process is to break down a document, a sentence, what we call a corpus of text, into what are called tokens. And these tokens, you can think of them as words. Though technically speaking, they can be parts of a word or even individual characters, but it's easier to just think of them as words. So the first step of tokenization is to convert the cat sat on the mat to the individual words in that sentence, right? So that's the first step in trying to get the text to be understood by the neural network, right? For example, in the Gemini model, 100 tokens roughly equals 60 to 80 words. Right. I'll come to why this is important later in terms of just practicality. So the next step is you take these tokens and convert them into what are called embeddings. So these are, each word is converted into a set of numbers, right? A vector in math, right? A vector is nothing but a list of numbers, right? So this vector represents the meaning of that token, right? So it's not some random representation of that word in terms of numbers, but it's a very meaningful representation. The way it works is the embeddings represent, for example, if two words are similar to each other, right, synonyms or close in relationship, then these vectors will be close together. Right? Think of vectors as lines in a graph, let's say, right? So if you have two words that are synonyms or very close in terms of relationship with one another, then these two lines will be closer together. If they're not, those two lines are going to be further apart. So these are called word embeddings, and the neural network essentially understands these word embeddings, not the actual text word itself, right? So there are many techniques to use to create these word embeddings. I'm taking a more higher level approach, not going into all the little nuances and details, but this is the intuition. This is really what it boils down to, really. The rest is all detail, right? So I mentioned that the LLM is essentially a transformer neural network, right? And the revolutionary concept or the seminal paper that actually transformed these LLMs let's say about 10 years back is when this seminal paper came out. The concept here is called the attention mechanism, right? And, what this allows the transformer model to do is to focus on different parts of the input sequence or the sentence, the input sentence or the multiple sentences, whatever it may be. It lets you focus on different parts of the sentence to understand the entire context before making the prediction of the next word, right? So as we all know, in language, context is everything, right? So you need to know the context to be able to come up with a meaningful prediction, right? So for example, if you read the sentence, the cat chased the mouse because it was hungry, the word "it" can refer to cat or it can refer to mouse. For us humans, it's easy. We know immediately, we know, right? But for computers to understand that is much more difficult, right? So this attention mechanism is a way where the computer learns the "it" refers to the cat and not the mouse, right? So these type of contextual relationships is important, and otherwise the whole thing won't work at all. Literally won't work, right? We know that as humans, it's just automatic for us, but for computers, that's a hard problem to solve, right? So this attention mechanism was a breakthrough that led to these modern day LLMs being so good. Any questions on this? Make sense? All right. So how do we train the LLM model? The training of a modern day LLM is a multi-step process. So it's somewhat similar to an educational journey where you start with basic language skills and then you build it on to understand and respond in such a way like humans would do, right? So each step is builds on the next and ensures that the output is some more like what a human being would have in terms of language, right? So the first step is pre-training. So here the LLM is exposed to massive amounts of raw text, right? So all the websites are scraped, you name it, all publicly available textual data is fed to this LLM, right? That's why these things take so much money and effort to train, right? They're trained on mountains and mountains of textual data. Then the next step, this is like, building the first pre-training phase is like building the basic language skills, right? So like grammar and sentence and, the English professors here would appreciate it, I guess. It's like the very basic linguistics skills, right? And then comes the supervised fine-tuning part. So here the LLM is shown different prompts and outputs to those prompts, right? So you have a large data set of curated data set of prompts and outputs, good outputs to those prompts, right? So, and the LLM is trained on these prompts and outputs to those prompts, responses to these prompts, to learn from what should a good response be, right? It learns, in the first step, it didn't understand what a good response should be. It just understands language, right? And then in the next step, it starts to understand, what should a good response be, right? Then the third step is what's called reinforcement learning from human feedback. So here we go one step further, and we make the LLM learn how we prefer our responses in terms of, for example, being, harmless and not spewing any inappropriate information and things like that, right? So this RLHF, or the reinforcement learning from human feedback, is important in terms of the LLM being able to provide well-structured human preferred responses that are not harmful. Okay. So how does the reinforcement learning work? So first step is we get feedback, human feedback. So the humans are presented with several responses from the LLM, and then humans rank the responses. If you remember way back when ChatGPT was actually introduced, they had the ability for us to go in and actually tell them what would be a better response, right? And they used all this to actually train the LLM, right? So that's the first step. We get the human feedback, we rank it, and this creates what's called a reward model. Okay. And the reward model learns to predict how we would rate a given response. So essentially, the reward model learns what makes a response very good, right? So the third part in this is where the reinforcement learning comes in. Reinforcement learning in and of itself is a broad field that you can have an entire course on reinforcement learning. Right? So you've heard of these game-playing robots or game-playing AIs, right? I mean, in the news way back, we had the neural networks playing Atari or Pokemon or the game Go, and they were able to beat the grandmaster at Go. These models actually use what's called reinforcement learning. They are all, based on reinforcement learning. And that's incorporated into the current day LLMs. The original LLMs did not have as much reinforcement learning in them. Now, the idea here is like, the analogy is like how a child would behave. For example, you give positive reinforcement to a child and it knows, okay, that's good behavior. And if you give negative reinforcement to the child, it knows that's something that is not what I'm supposed to do. That's the same concept here. The reward model actually presents a reward signal to that LLM. And if the LLM produces a response that humans would like, then it gives the LLM a positive reinforcement, right? And if it doesn't, then it gives it a negative reinforcement or a negative reward, right? That's why it's called a reward model. It's actually giving these rewards to make the LLM behave in a particular way, right? Just like we would deal with a child by giving the child, we implicitly actually give children positive reinforcement and negative reinforcement, right? So it's the same idea here. Any questions on this?
Yes, Professor J.D.
Yeah.
I have a question. I've been following you, and I think I have a little bit of a concern. You talk about like being like harmless, and then how we can reduce like a bias. Because if you see, sometimes when we build a model, we can have some like a bias, and with the AI, with the also we see algorithms plays an important role. And if we start already in the beginning of the model with some bias, it seems like it's going to repeat itself, keeps going. And I'm saying that, like, let's say I want to build a model, and also, to apply it to some culture, and if like in the models there is some bias, sometimes I'm asking how can I actually reduce that bias, because you talk about in your previous slide about actually minimizing the error. And I was thinking maybe the error has to do with the bias and all of these things. So yeah, I'm wondering like how we kind of reduce like some bias, and then
Yeah.
like the algorithm can repeat.
Yeah, where does the bias come from? Typically, the bias comes from the data, right? So, for example, you just use data from one demographic or one ethnicity to train the model, then that model is going to be biased towards that, right? So, one way to reduce bias is to make sure the data that's used to train the model is in of itself unbiased, right? So the bias in models is again an entirely big topic that we can talk about. There's still ongoing research, and it's not a solved problem by any means, right? It's this bias can creep in many ways. One of the biggest ways is from the data itself that's used to train them, right? So let's go forward. All right, sorry, do we have another question or?
Yes.
Yeah. Hi. Sorry, but my camera I don't have good light right now. One thing that I want to mention is that it's interesting the point that you are making. However, you are not including two important variables, and those are power and representation. Unfortunately, the people that are generating the data and creating these models, not everybody is represented. There are groups that are not represented, voices that are not there. That's one issue that I see. The second issue that I see is power. The people that are in charge, creating these models and are managing artificial intelligence, are people in power. And they are using that power to generate models that fit their ideas, but also that support their biases. So
yeah, totally agree. Yeah, totally agree that
if we talk about, I'm an anthropologist, so for me, it is relevant that we acknowledge the fact that emotions, feelings, and perceptions are something that is still AI cannot, or is still we're working in how AI can begin to incorporate as part of their, environment. And one phrase that I would like to mention that is part of literature, but also we're using in anthropology, is the notion of an endless place of significance. If we look at the way in which programming works on assigning a binary or non-binary meaning to words, one thing that is missing there is the significance, the multiple versions that the individual can provide to the meaning of a word. And AI still is having problems, trying to identify significance for specific groups, particularly groups that are minorities and they are not represented. So do you have any comment on how we are working to resolve these issues?
Yeah, I agree. There's still the representation in the AI field needs to be improved, even in terms of gender representation, ethnicity representation. That's an entirely different topic. In the interest of time, I'm going to move forward. I unfortunately have a ton of information, but I don't think we'll get through it. But let me try to. That's a conversation we can have. We can talk for hours on that. There's lots of a debate we can have on what the bias, the ethical issues, but I'm not focusing on those type of things. This is more to understand how the LLMs work and what can you do to use them better. Okay. So the next step is inference. How do we generate the new text? So once the model is trained, we need to generate new text, and this process is called inference. Right? So what we do is we give the model an initial prompt, and the model predicts the next word or the next token. And then we feed that token back and have the model predict the next token, and so on and so forth. So this process keeps continuing until the model generates a complete text. So the way the model chooses the next token is called the decoding strategy. And some decoding strategies include greedy decoding, which essentially boils down to always take the token or the next word that has the highest probability, right? And the other approaches are via sampling, where a token is based on sampling from a set of words, right? And another approach is called beam search, where you keep track of multiple sequences and then choose the best one at the end, right? So this defines how the output is produced, right? And immediately you see that when this is what makes the LLM generate slightly different input each time you run it, right? Because there's a probability involved and there's sampling involved, right? So each time you run the model, you can get a slightly different output. So this process is called the decoding. So the last thing I want to touch on before we move into how do we use it better is some terminology and parameters that you probably have heard of. Model size. This is how many parameters or variables or the knobs that you can turn, right? And nowadays, these things get bigger and bigger and bigger, right? Even today, the ChatGPT launched ChatGPT 4.5. And that's supposed to, they don't disclose exactly how many parameters, but people are saying that has somewhat like 1.5 trillion or 1.8 trillion parameters, right? So imagine having 1.8 trillion knobs to turn. Right? That's kind of the size of these models nowadays. And the more bigger the size of this model, in the conventional wisdom so far has been, the better it is, right? And that's starting to change with these models like DeepSeek, which you heard in the news, that's actually doing more with less, actually. Right. So the other terminology here is a context window, which is the maximum number of tokens that the model can process at once. A large context window allows the model to understand more complex relationships, right? So for example, ChatGPT 4.0 has 128,000 context window, right, tokens. So this is important for how far back the model remembers and so on. Output token limit there is important because that limits the size of the output that the model can generate. So for example, ChatGPT 4.0 has 4,096 tokens. Gemini has 8,192. Another parameter is called temperature, and this controls the randomness of the output. So if you have lower temperature, then the output is more predictable and deterministic. If you have a higher temperature, the results are more random. And then the last one is tokens per second, which is how fast can the model produce the output. Right? All right, so that took longer than I expected. So, in the next 15 minutes or so, I'll try to cover what I can with respect to how we can use these models better. One of the most important things that we can do is what's called prompt engineering. And this is the practice of creating a prompt very carefully in a very deliberate way so we can get the best response from the large language model. Right, so prompt engineering is key to unlocking the potential of LLMs. So what I'm going to go through is in the next, there's a lot of information on prompt engineering, and we probably only have about 10 minutes left. So I'll try to illustrate some of I'll probably skip a few things and just highlight some important things. And if people are interested, we can come back to this another time. All right, the simplest prompt that we typically end up using is what's called a zero-shot prompt. And here we just give it an instruction, basically, right? Like explain what machine learning is in simple terms, or develop a key question that could be used to test the understanding of. So these are examples of what are called zero-shot prompts. This is the simplest type of prompts, and most of us end up using such simple types of prompts. But these prompts are not ideal, right? They do not unlock the potential of the LLM, right? Though they will give you good outputs. I mean, they'll give you an output, but you can do better. So how can you do better? So here's a framework for creating good prompts. The acronym here is thoughtfully create really excellent inputs, right? So that stands for task, where you describe the task in a very clear and deliberate format, and context, you give it a lot of context, right? And references, here you provide lots of examples for the AI, for the LLM, right? And then you evaluate the output, and then you iterate, right? So this is a broad framework for creating good prompts. Again, this is very generic. It doesn't necessarily apply just to faculty or to educational use or anything. It can be used for your personal reasons, for using the LLM for whatever you need. So for example, you can write, how was DNA discovered? Instead, you would be better off writing like this. You're a science expert developing a new curriculum at a local college. Tell me in a couple of engaging paragraphs how DNA was discovered and what kind of impact it, you give it a lot of detail and a lot of context and a lot of examples. And you would see a vast difference between what output how was DNA discovered, generated, versus what this prompt would generate. Right. So I'll skip that. So the way we approach prompt engineering is by describing a lot of prompt patterns, right? So we describe these prompt patterns in what are called fundamental contextual statements, where you give it the instructions that the important instructions that large language model needs to know to generate the desired output, right? So there's a lot of patterns that are available. Since we're running short on time, I'll skip around a little bit. One of the patterns that's quite simple and that we don't usually use when we do the zero-shot prompting is we give it a persona, right? That's called the persona pattern, where you say act as some persona, right? So act as a biology professor, or act as an expert in machine learning, or act as a nutritionist. So you give it a persona, and then the AI takes on that persona and gives you better responses. Similarly, you can give a persona for the audience, right? Assume that I'm a 5-year-old. Assume that I'm have no knowledge about machine learning, right? So you give it audience persona, and it produces much better output that's tailored to what you want. Right? Another important prompting technique is what's called few-shot prompting, or it's also sometimes called in-context learning. Right? So here, the few-shot prompt involves providing the LLM with a small number of examples that it can learn from. Right? So you give it examples of inputs and outputs, and ask it to use those examples that you gave it, right? And this makes a big difference in the output, right? Zero shot means you didn't give it any example. That's why it's called zero shot. And one shot means you give it one example. Few shot means you give it a few examples, right? So typically the rule of thumb is you give it at least 3 to 5 examples, right, for it to. So for example, here, this is a few-shot prompting example where you are generating hypothesis, for example, right? So the prompt reads generate research hypothesis based on the following pattern, and you give it some examples. Context, increased screen time among adolescents. Hypothesis is increased screen times is correlated with increased levels of anxiety and depression, so on. You give it a bunch of examples, and then you give it the last one, which says the impact of climate change on coastal ecosystems, and then it will generate a hypothesis based on the examples that you provided. Right? I can show you in ChatGPT, but I have all these prompts, examples set up in ChatGPT that I was going to show you, but again, we are running short on time. So I'll skip that. So here's some more examples of few-shot prompting. So few-shot prompting for creative writing. You can give it story beginnings and continuations and ask it to do something similar to what you provided, right? So this is a way of really tailoring the response to what you need, right? Instead of giving it a broad prompt. All right, let's skip these. All right, and one of the questions we were just talking about is the the hallucinations in AI and ethical things and so on and so forth. So one of the patterns that you can use in that case is what's called a fact checklist pattern. right? So you essentially give it some constraints, basically, right? Uh, so you say, whenever you output text, generate a set of facts that are contained in the output. That a set of facts should be inserted at the end of the set of facts should be fundamental facts that could undermine the veracity of the output if any of them are incorrect. And if you give this type of a prompt, then the LLM will actually give you facts that you can check for yourself, right? So this way, you prevent too many hallucinations. I mean, you cannot totally avoid the hallucination, but again, this is, at the end of the day, we have to evaluate the output, right? It's not something that, so there is a human in the loop always, right? In my mind, AI is an augmentation tool to the human. It's not necessarily a completely independent tool. It can be, but most of the best uses will be with working alongside a human. Okay. So this is something I wanted to point out since we had that discussion. There is in the next few minutes, let me just go to the end and so one of the things that people don't probably realize is you can actually do a lot of data analysis with LLMs, right? That's something that the LLMs, when you have the ability to code, so in fact they are really very good at coding actually. So when you give them data, they're actually able to generate code and do all sorts of analysis that you couldn't imagine before, right? Being done automatically with just prompts, nothing else. You don't need to know any coding. You don't need to know even anything about the statistical methods or anything that you want to use. You just give it verbal prompts and it's able to unearth a lot of patterns and insights from the data very easily, just with language, just with English prompting, right? All right, so let me skip to the end where I had some thoughts on how we can use it in terms of teaching and learning, right? So some of the teaching strategies can use AI to produce very many examples, right? Students learn better when they are provided with lots of examples, but generating lots of examples is a very time-consuming effort for teachers, right? So you can use AI to produce many, many, many examples that can help the student learn better. Similarly, you can use, when I say AI, typically AI and LLMs nowadays are used interchangeably, though AI is much broader, to provide multiple explanations, right? Certain complex concepts, one explanation doesn't necessarily get through to the student, right? So you can generate multiple ways of explaining the same thing through AI. And lots of times, even I've been surprised when I teach, I'd say it in a particular way and explain it in a particular way. But when I ask the LLM to give me different ideas, I'm always surprised. Oh, I could have done this. I could have done that. I mean, even with years of teaching the concepts, I still get surprised that, hey, this approach makes, I never thought of this before. Right, so it's very, very interesting and makes teaching and getting through, especially difficult concepts, through to the students makes it much easier. Another strategy that these are all, evidence-based strategies, right? So if you look at the education literature, there's lots and lots of evidence for learning improvements due to examples, all these are based on evidence-based. They're not just off the cuff stuff. Right? The low-stake tests. We know that students learn better if you give them multiple low-stakes tests, right? So again, that's time consuming to generate so many low stakes tests, right? It could be just generate a small quiz with 2 multiple choice questions or 2 fill in the blank questions, and the AI can generate tons of those for you within minutes, right? So that's another thing that you can do. And another strategy is to distribute practice of important ideas. And this comes from, again, the teaching and learning literature, education literature, where you want to distribute practice across the entire course so that students can tie back what they learned in a later part of the course to the previous part of the course. And you get to make those associations. And that makes your learning much better, right? A lot of times we end up, as students progress through the course, we don't test them on the previous material, right? We just keep testing them on the newer material, right? But it's important to test them on their entire knowledge because that helps them make associations between this different concepts. And so that can be done easily with the help of AI. Again, these are not just the AI doing it, but you using the AI to do these things, right? Approaches for using LLMs in the classroom. LLM as a mentor in terms of providing feedback, right? There you can create all these, I have these examples. Unfortunately, we don't have the time to go through these examples, but you can create a role-playing game, right? For example, you want to learn Spanish, right? You can create this a Spanish instructor role play, and then ask the LLM to give you questions, and you answer them. The LLM gives you feedback, and you can use this for many things, like practice negotiation skills, practice your ability to code even, right? So there's many uses for that. And providing direct instruction, which is LLM as a tutor, LLM as a coach, where you increase, all of this is again rooted in evidence-based literature, right? So LLMs as a coach, where you're increasing metacognition. Metacognition is, typically people say learning about learning, right? Where you have self-regulation, and that helps a student actually learn better, right? And the LLMs can be used as a coach, where it guides the student to reflect on what they did, right? That reflection is that metacognition. LLM as a teammate, where you use it collaboratively, and it improves collaborative intelligence. LLM as a student is an interesting use case, where you ask the student to actually teach the LLM, right? So, the student as a teacher, again, there's a lot of literature to show that when students teach somebody else, they actually learn really well, right? So this is that idea. And the last thing is LLM as a simulator, right? So you can use the LLM as a simulator for practicing various things, right? So your students can practice. So again, I have lots of examples of these. Unfortunately, we're out of time. A good resource is this website I have here, which if you can look at it, it has lots of good examples of prompts and how we can be used for instructional purposes, pedagogical purposes. This is a Wharton professor called, his name is Ethan Malik. So this is based on his papers, his research. So again, rooted in evidence-based learning. All right. Unfortunately, I couldn't cover all the material I wanted to. I kind of so if people are interested, we can always come back to this. But I hope you got something out of this and something concrete out of this that you can use. Feel free to reach out to me if you want to discuss anything further. Right. I don't know, Carolyn, what do we want to, I have some more time if people want to ask questions, but if we want, I know we're out of time.
Yeah, I mean, I think if you have some more time and if anyone wants to stay on and ask questions, I also have time too. So I'm